Yeah. So, hello everyone. I'm Vishal. Are you able to hear me? Can somebody unmute yourself? Okay. Okay. So what we'll do, we'll just go through the first, third, and fourth week in brief, because we have already done the revision session for the first quiz also for all these weeks. So we are just going through the first and third and fourth week. We'll just tell you the some important topics that is the most important, and we'll go through the all the concept briefly, not in the detail. If you have to go through the detail, you can go through the last lectures, or the last, you can say, the search lectures and all. So we'll just go through the, yeah, good evening, Kodas. Okay, so I'll go through that. I'll just share my screen. Are you able to see my screen? Are you able to see my screen?
Yes, Vishal, we are able to view your screen here.
Okay, so in the first week, we just talked about a basic like ML. What is ML? What are the what are the different types of algorithm? What are regression? What are supervised learning? What are unsupervised learning? What are classification model? What are regression model? And we have just talked about the in the end, we have talked about two unsupervised techniques, that is dimensional reduction, and one was the density estimation. Okay, so we'll just go through that. So ML is simply a study of algorithm that improves automatically through the experience of the user data. As big or as much data we are having, the algorithm or the model which we are developing will become a better and better. Okay, so for example, we can have models like car rate predictor or the weather predictor and all. So car rate predictor can be a regression model. So we'll just discuss a brief about the regression also. So why we are doing generally for the speed purposes or the cost of human labor becomes very large if we'll allow the human to do that. So it's become a cost efficient also. The speed become very fast and all. So these are the some important regions regarding this. Just for the conceptual purpose, we'll just talk about a features data set. So this is data set where we are having a features one, feature two. So this is a simple data set having the three features and having the label. Label means the output, or the output in the final outcome also we are having. So this is the label simply. So for example, this is the we are just this is the data set of phone. This is the phone rate predicted. Okay, so we are having the features like we can have the RAM, what's the, and the storage capacity, and the size of the screen. Okay, so these all things, yeah, these all things can be the features of the size of the screen. And these are, we are having three observations. So this is the first observation, this is the second observation, this is the third observation. We can have millions of observations based on this, and then we'll be having a label. So this is a data, simple data set with the three features and the label also. Okay, so model is simply a mathematical simplification of the reality. So types of ML algorithm, we generally, broadly speaking, we are classifying all the ML algorithm into supervised and unsupervised. So there are others also, but here we'll just talk about the supervised and unsupervised. So in the supervised learning, we'll be having this depends on the data set. The data set, if the data set having the label is present, like the final outcome is present, then we'll say that then we'll say in this data set we can work with the help of supervised learning algorithm. And also this supervised can be of two types. This simply the regression or the classification. So regression is those sort of data set, or those sort of like supervised regression are those things where we will be able to apply where the labels are generally continuous. Like for example, we have talked about the price predictor of the phone or the price predictor of the car sort of thing. So where the label is continuous values, the continuous means any value can come here. Some there should be some sort of range also, but in the regression, the label is simply the continuous. Okay, and the loss function is simply yeah, and the regression is this one, and the classification is where the label is simply in the term of yes or no, or you can say in the term of -1 or 1 or 0 1, some sort of yes or no sort of things. Like if we have to classify, like if we have to classify in 3 types, like for example, if we are having a data set of the Alzheimer patient, so whether this is a normal patient or he's suffering from some mild cognitive or like the second stage or he's in the third stage. So this is also example of classification model. Okay, so here the loss function is simply for the continuous like regression, sorry, for the regression supervised learning. So generally we have the loss function in this form. Okay, so where this is the actual and this is the this is the predicted one and this is the actual value, and we can calculate the loss with the simple example. Okay. And then if we have developed many more, like if we have developed 2 models, F and G, those models are F and G. And in this model, if we are calculating the loss, and if the loss for the F function is less than the for the G function, then we can say the F is a better one than the G. So this simply implies that whichever the models is having the less loss function will be a better one. Okay, and simply for the classification also we have the loss function, but in the classification we generally sort of, you can just add the like wherever our model is not predicting correctly, and you can add them and divide it with the number of data set of the observation how many you are having, so you'll get the loss function for the classification. And here also, if you're having some sort of models where the loss is less, then you can say this model is a better one. Okay, now we can say there are generally in the data set itself, we generally classify those data set into 3 parts. One is the test data set, the training data set, and the validation. So the training is those data set generally on which we generally train our data set. Okay, so we can have 1,000 of data set and we can classify 60, 20, 20, and then from the 60% of the data set we can just train the model, and then we can validate, like we can validate on the 20%, like we can do some sort of, we can select the models out of that by doing some of the hyperparameter tuning and all, and then we're having some chunk of data left for the testing sort of things. Okay, so we can test our model on the 20% of the data set. Okay, and then we'll come to the unsupervised learning. So on the unsupervised learning, generally we don't have the level, like in the the final outcome we don't have, we just have the data set. Okay, we have to group the, like for the Alzheimer patient I told you, in that Alzheimer patient data set, if we don't have the levels, the final data set, like for example, if I'm having the MRI for 1,000 people, okay, in the MRI, if we have just taken out some of the inputs from the MRI, but we are not aware of the final result, whether this MRI, whatever I'm having in my hand, is this person is normal or is in the first stage of the Alzheimer, in the second stage of Alzheimer. If the labels is not present, then we can say this is unsupervised sort of learning. We have to use some sort of unsupervised learning. Okay, slow please. So okay, so in the unsupervised learning, you don't have generally the label. Okay, now here we just have to understand the data. Okay, and understand the basis of understanding the data, we can cluster those data clusters those data in one group or the other group, sort of things like that we can do. In that unsupervised learning, like here we generally are compressing our data, explaining or grouping our data. Okay, so here in the unsupervised learning, we generally use dimensional reduction and the density estimation. Here we have covered these 2. So there are many others also, clustering and all, but we have just limit ourselves to the dimensional reduction and the density estimation here. So in the dimensional reduction, what we are doing, if we are having a very large dimension, we are just reducing it. So it is just dimensional reduction simply means we are compressing and simplifying. So we generally have the 2 things, that is the encoder and decoder. Encoder generally help us to compress the data set, that will help us to make the system as memory efficient. Like if we are having a very large chunk of data, so we can just compress those data set, and then we can use the decoder also to undo that, and then we can utilize those sort of data set. Okay, and now here what is our goal? Here our goal is, whenever we are doing the encoding and decoding, after encoding and decoder, whatever the outcomes we are getting, that should be almost similar to the starting data set. This is our goal here this is our goal here. So that's why we have written approximated value. Okay, and so loss also here can be calculated. So the initial value and the final outcome value. So those error chi-square upon n, we can get the loss function. This is pretty like same as the loss function, loss values we are calculating for the, what you can say, the regression thing. But here you'll get sort of like the formula is almost same to the final outcome of minus the initial outcome. Okay. And then just divide with the number of data points you are having. Okay. And the final thing is the density estimation. So density estimation is simply used whenever we are having a chunk of data set. Like for example, I told you for the Alzheimer patient, if you are having only 500 MRI. Okay, so but for the 500 MRI, we can't build a very good models to, we can't build a very good model to predict anything. So what we'll do, we can from that 500 model, like for example, if for that 500 model, if the like we were having that MRI, okay, and out of that MRI, I have taken out the some sort of inputs, like I've taken out 5 features from that MRI. Okay, from each of the MRI, I've taken out the 5 features. So for example, one example can be a gray matter volume for from of the, what you can say, the gray matter volume from your brain or mind. Okay, so those sort of, this simply that like the volume of the hippocampus. So those sort of 5 features can be, I can take out from that MRI. Okay, and those five features will be having some sort of probability density. Okay, what you can say, the distribution. All those 5 features will be having some sort of probability distribution. And after reading the probability distribution of each of the features, we can take out a number of more what you can say, the data set. Right? For example, if I'm having that what you can say, the 5 features I was having, like for example, I've told you 3 features only, and each features will be having some sort of probability density distribution. Okay, so if for example the features F1 was having this normal distribution, so and with the 500 data set, with that 500 data set, we can simply this 500 can work as a sample data set. And you already have read in the stats too also, and here also in the CLT theorem or many other places also you would have read, out of that 500 data sample points, we can predict, we can estimate the value of the mean and variance, and then we can know regarding the distribution. And out of, and if we can know regarding the distribution of each of the features, we can take out a large number of data sets from those features, and we can build a good model. Like for example, if I was having already 500 observation earlier, okay, out of that 500, so now we have made out of that 500 observation, we can make 25,000 observation we can take out, okay, from that distribution, and then we can build a good model. Why we are doing this? Because if the MRI can be computed for many of the person, but again it will become very costly to take out the MRI for so many patients, and also it's better to, if we can exaggerate those data points whatever we are having. So this is one of the best, what you can say, not best, the one of the implication or the example application of the density estimation. So here also loss is this, simply this one, this negative of likelihood function, and then you can divide with the data number of the data sets. Okay, this is simply used for the increase the number of the observation. This was it for that. And yeah, so what is the most important thing that you should know for the calculative part is to you should be able to calculate the loss for like for example, if you have been told for the regression, or if you have been told for the classification problem, or for the, what you can say, the dimensional reduction. Okay, very less chance to give you it's very less chance to get for the density estimation, but the classification, regression, and the dimensional reduction, for those 3 you should be able to calculate the loss function. That is pretty important, that I have mentioned here also. So what you'll do is, for at least for the first week, you should be able to calculate the loss function for all the questions they're present in the graded or the practice or wherever it's there, or you can say the last term question. So just try to solve all those loss function, and the conceptually this week is pretty simple. So I don't think so there will be any issue in that. But yeah, so try to solve the loss function for all the like previous year papers also, and this time like the practice and graded also. And if you're having any issue related to first week, you can ask. Otherwise, we'll move to the next week. Yeah.
Sir, I have a doubt for validation data. What is the purpose of that?
So many a times what happens, we have built a model based on the training data set also. Okay. And if we are same thing we are doing in the validation, like the validation can be helpful. There are many other things like the different parameters generally we use in the models. Okay. Like for maybe you must be knowing regarding the like the parameter, different parameters are there. Like for example, if I'm working on some sort of random or dysentery sort of like a model, okay, algorithm. So in that, generally we have to take out the optimum value of the leaps that will end in the model. Okay, so or the starting portion, how many leaps you are taking out. Okay, how it should be splitting from the starting point. So on the basis of training data set, you are doing that, you are training the model. But for out of that training or out of those models, if you need to take out the one of the good suitable models, will be that validation data set can help you to give you the optimum value of the number of leaps or the different hyperparameters that are available for that model. Okay, so the validation part will help you in that, and then those things can be doable. You can, what you can do is to predict the value for the test data set. That will help you to give you a better accuracy sort of thing, because those test data set is not visible to the model, right? Because hyperparameter tuning also you can't do in the training data set, because training data for the training data set, it's the model has already seen all the data set. Okay, so it's better to give some new data set and then predict, and then on those prediction tell the model to give you a good hyperparameter value. Okay, so that's why we are that's why we are generally splitting the models in 3 parts, not in 2 parts. That is training or test data set. We are splitting those in 3 parts to get a better models out of those models. Maybe this would have made you clear.
Yeah, okay, to find the best hyperparameters, right?
Yeah.
Yeah, okay.
Sir, I have a little doubt on the present, means the level is not present in the data in unsupervised learning.
Yeah.
Sir, can you give an example for that?
For the last week, you would have read like GMM model or clustering model we read, right? There was no label. So we just have to, with the help of expectation maximization method, we were just grouping those data set. Have you remember? Are you able to remember that?
No, sir.
In the clustering model, see, for example, I'm having an Alzheimer patient data set. Okay. Okay. So if I'm having an Alzheimer data set, in that I'm having a 500 observation of the patient, and I'm having only the features like F1, F2, F3, and I don't know regarding the patient is either this patient is the Alzheimer patient or the normal patient. So we don't know regarding the label. Okay, we just have the features, and that features we have extracted from the patient's MRI. Okay, that patient can be normal, can be the Alzheimer patient. So we don't have the label, the final outcome of that. Whether if for example, I'm telling you, if I'm having the label, for example, this label for the first patient is 1, that means the patient is the Alzheimer, having the Alzheimer disease. Or for the second patient, this label is 0. That means the second person is normal. So this label I don't have. Okay, on the basis of this data set only, I need to read and I need to group those data points. I need to group those patients. Okay, this, like for example, I'm just representing, if this 500 data set I've represented on the what you can say, the 2-dimensional thing. Okay, so this outcome, this I've just plotted the scatter plot of this. So we have, now we can see that this is generally a 2 sort of like, this data set can be clustered into groups, right? But we can't say regarding which one is having the disease and which one is not having the disease. But at least we are able to see that grouping part, right? So this is simply the unsupervised sort of things. Okay.
Okay, so means in unsupervised we can't specifically say that it is a level
Yeah, we don't have the label, we don't have the outcome. You just have been given regarding the data set. You have not been told about the final outcome. Okay, you just have the data set. On that data set, you just have to understand. You have to understand that data set. On understanding on that, just you have to understand those data set and come to a conclusion. Are you getting my point?
Okay, means we can't get any conclusion about that.
The conclusion is not been given. You have to
Yeah.
go to some conclusion on the basis of the data set one. Because see, if this all data set like the 500 observation we are having, and some patient will be normal and some patient would be having the disease. So those features will be different for sure, right?
Yes.
Okay, so on based on those features, you have to build a model and we have to cluster those things. So this was there in the last week. Maybe if you'll go through that, the last lecture, sir has talked about one model, one clustering, what you can say the algorithm, that is the expectation maximization. He's talked about that. Maybe that will help you. But this was pretty simple. You just have to categorize. If you're having the label, the final outcome, you have to, if you are having the final outcome, you have to use some sort of supervised learning algorithm, and if you don't have, you can use the unsupervised learning. So there are many. We have talked about only two.
Understood. Thank you.
Okay.
So one more thing, is density estimation used to create synthetic data?
Yeah.
Is it so?
Yeah.
That's correct, right?
Yeah, it's correct.
Okay.
Okay, if you are having any other issue, otherwise we'll move to the next week. And the important thing I've already told you, just go through, like at least try to solve all the questions related to the loss function. Okay, I'll move to the next one. Amrita ma'am, are you there?
Yes, Vishal, I'm here. Yeah, thank you for the session.
Okay, thank you.
So you have informed, right? Week 2 will be handled in the next
Week 2 we will be discussing the next session. So we will discuss here 3rd and 4th week now.
Okay. So if they have no more questions, then shall I share my screen?
Yeah, you can share. I'll stop sharing.
Okay, thank you. Okay, so is my screen visible to all?
Yes, ma'am.
Yeah, okay. So let us quickly go through the contents of week 3 Machine Learning Foundations course. So in week 3, we introduced this linear algebra. So in linear algebra, the main basics are with the 4 fundamental subspaces. And we saw the relationship between orthogonality and vectors and orthogonality of subspaces. And the third topic was projections. And finally, it is ended with some least squares projections. So in 4 fundamental subspaces, we already know that the column space, row space, null space, and left null space are the 4 fundamental subspaces. So for any given matrix of size say m cross n, the column space of A is a subspace of Rm. So how do you say it is a subspace of Rm? Because if you consider these columns, so a matrix is made up of many columns, right? So these column vectors consists of m elements. So it is in a subspace of Rm. And this row space is can be computed through column space of transpose of the matrix A. So in that case, see, this is your row, right? So your row has n components. So therefore, it is a subspace of Rn. So you should remember, you should not simply write it is a, since there are n number of columns, the column space does not consist of the subspace of Rn. The number of elements in the column vector matters. Okay. So remember that the column space is a subspace of Rm and row space is a subspace of Rn. And the third subspace is the null space. So how do you compute this null space? So null space is the vectors that give your product with your matrix as equal to 0. So these vectors, so the solution for this equation Ax equal to 0 constitutes of your null space. So this vectors are in dimension Rn. So therefore, the null space is a subspace of Rn. And the last subspace is left null space of the matrix, which is the null space of A transpose. So therefore, we can write it as Y transpose A equal to 0. Or you can also write Y into A into Y is equal to 0. So this is the solution of this equation. Hence, those vectors which gives product as 0 when you are multiplying with the matrix A constitutes your left null space. And since these are in the transposed for this null space, it is in a subspace of Rm. So these are some simple fundamentals of the 4 subspaces. So the next topic is based on the orthogonality of the vectors and subspaces. So in general, you know that for this any vector x and y, if you want to say these two vectors are orthogonal, what you do? You just take their dot product and make it as equal to 0. So when
Hello.
I think we
Yeah,
seem to
one
have lost
second.
our internet connection. Yeah, let's wait.
Yeah, 1 second.
fulfill, then we say that these two vectors are right. Hello, can you see my screen, Vishal?
No, not
No,
really.
ma'am.
Like, there was
Oh,
I
sorry.
guess, yeah, there was a,
So connectivity problem, I think.
yeah,
So,
yeah, there was a net.
okay. Just now I realized. So, from which part?
Last 1 minute.
Last minute. So, did you get my point for orthogonal vectors?
Yes, you lost
Yes,
in
yes.
product.
Dot product 0.
Okay. So, the dot product of any two vectors to be 0, then those two vectors are orthogonal to each other. So now, how do you say that two subspaces are orthogonal to each other? We say that if this row space is orthogonal complement. So this is this belongs to orthogonal complement. So what is an orthogonal complement? Which means, so in a subspace, there may be more than one or two vectors that belong to a subspace. So when we say that it is an orthogonal complement, then it means that each and every vector in one subspace is orthogonal to each and every vector of the other subspace. So that is why we say that the row space is an orthogonal complement of the null space of the matrix. So this you can also verify with their dimension. And similarly, the column space is an orthogonal complement of this left null space. So how you can relate it? So while you compute this row space and null space, so when doing so, this null space is also in the rows of the matrix of A. So hence they both have the same dimension. So similarly, that applies for your column space. So this gives us the rank nullity theorem that says that the rank of a matrix minus this dimension of the null space gives you the nullity of a matrix. So this is what, so the important point that you remember in between these subspaces is this one. The row space is orthogonal complement of the null space and the column space is orthogonal complement of the left null space. In projection, so what do we learn from this projection? So when you have two vectors, that is vector A and vector B, and if you want to project this vector B onto this vector A, you get an error. That is, this error is the difference between this vector B and its projection P. So that is why E equal to B minus P. And this error vector is orthogonal to this A vector. So from that property, we get that the projection vector is equal to A transpose B by A transpose A into A. So this is what the formula that we have derived from the lecture also. So if you want to calculate a projection, that is, this is the projection. So in this vector A, so this part alone, so this is the B. So this is what you get while you project this B vector onto this A vector. So this projection is equal to this dot product between this A and B divided by dot product of the same A vector and multiplied by your A vector. So this will give you a scalar value, whereas this when you multiply this with this, so now this A is one vector. So finally your projection is a vector. So remember, how do you get this vector? So the projection matrix, so from this computation we arrived at a projection matrix. So to compute this projection matrix, we know only the vector alone. So given any vector, you can compute its projection matrix, so that if you want to compute its projection, that is simply if you are given with any other vector, that is B, the projection of that vector onto this A vector is equal to this projection matrix multiplied by any vector. So if you are provided with one vector, you just find the projection matrix of that vector and keep it aside, so that if any other vector is given, we can simply multiply that with the projection matrix. No need to find new scalar vector products to find this projection, so that it is easy for this computation. So you have learned some properties of this projection matrix. So that is the square of projection. That is, since we are already projected onto this A, once again you are going to project. So that will lead to the same projection, because once you are projected from one vector to another vector, so it is going to stay in that vector space itself. So no, when you are going to project it again, then that is also going to be staying in that space itself. That's why we have P squared equal to P. And from the computation and from similar problem solving, you would have got that this projection matrix is symmetric. So that is the projection. So remember, when you are asked to find any projection of one vector onto another vector, you use this formula to find this projection. And if you want to ask find any projection matrix, we simply use that vector alone. No need to use another vector. So last and final topic in this week is regarding this least squares method. So why do we go for this least square approximation is that, we are having some set of data points in some d-dimensional space. For example, let us take in R2. So this is a two-dimensional space. So let us assume that there are two features, x1 and let us just assume that we have only one feature, that is x, and this is your y. So simple, how there are some data points here. So you want to represent these data points mathematically. So you want to have some model. How do we represent these data points in a linear way? So this least squares method gives you some linear approximation. That is, we map these points to a line. So that is straight line. This is your linear line that is equal to y equal to mx plus c. So our objective is we are going to find such a line such that the error in the representation is going to be minimum. So that is this line. So this is the least square solution. So b minus ax hat whole square equal to the minimum. So we cannot make it to be 0. So how you can make it to be 0? So if you want to make it to be 0, then you need to find a line such that it maps all the points, right? So only if there is some curve or something like this, that will give you an error to 0. But we are not going to use such line. We are going to form a straight line. Of course, you can see that there are differences between this point and this line. So that is why we are having the error to be very minimum. So that is why it is given. So why do we go that? Because the usual reason is there are too many equations. That is, the matrix A has more rows than number of the columns. So this is one you remember, because if you move further to ML techniques or ML courses, you will find some interesting data sets wherein there may be many observations. So observations in the sense, if, for example, observations are the number of data samples, right? So if you have more number of data samples, but lesser number of features and less features. So imagine such cases. So this is what corresponds here, right? When you say the matrix A has more rows than columns, it means the matrix, the data set has having more number of data samples, but less number of features. So in that point, in such cases, the m is greater than n. So there are rows are greater than n. So we cannot have this solution directly. That is ax equal to b. Hence, we are going to model this using least squares approximation of finding this line equation y equal to mx plus c. So we are going to find this m, that is the slope of this line, and c, which is the intercept of this line. Okay. So this is the least squares method. So how we solve this method is using that projections formula. So some solved problems, let us see. Here for fundamental subspaces. So given this matrix, you concentrate here on this matrix. So what will happen to find the column space of this matrix A? So first you need to reduce this matrix to an upper triangular form. So how do you obtain this upper triangular form? You just locate your pivot element entry here. And then in this first row, this is the first element. So we have to make the remaining elements in the first column to be equal to 0. So this R1, R2 and R3 are there. So we can simply consider this R2 as a 2 times of this R1. And this R3 is directly, you can just add R1 and R3, you can get a 0 here. So you can get 0 here and then 0 here. So by doing so, you will get this upper triangular matrix. So from this upper triangular matrix, so this is the pivot element. So how many pivot variables are here? Only one. And these two are free variables. That is, these two columns are dependent on the first column. So comparing this pivot element with this matrix here. So this first column is your only element in the span of your column space. So that is where we get span of 1, 2 and minus 1. The column 2 and column 3 are simply some linear combination of this column 1. So that may be some scalar multiple because there is only one vector in the column space. So a scalar multiple of this vector will give you the other columns. Now for considering this row space of this matrix A, I have taken this transpose of this A matrix and then found this row space. So in that case, transposing this matrix will give you 1, 2, minus 1, 4, 8, 4, 2, 4, minus 2 in the rows. So if you consider the same row reduction step, you will result in this matrix. So this upper triangular matrix has also only one pivot element and the other pivots are, other elements are dependent on this first column. So how do you consider this row space? So when you consider this row space of column that using this A transpose method, so the row space corresponds to the first row. So which is this 1, 2 and minus 1 because that is what being transposed, right? 1, 4 and minus 2. So this is what is transposed to. So therefore this row space is a span of 1, 4 and 2 alone. The other rows are some scalar multiple of this vector. And for the null space of this matrix. So considering this upper triangular matrix, we have one free variable. So therefore we need to find the solution for ux equal to 0 where this u is 1, 4, 2. So I can write my x1, x2 and x3 here for this x vector. So considering this x1 as a pivot variable and x2 and x3 as free variables so that you are free to choose. So therefore you can find this x2 as 2 basis entries and x3 equal to 0 for one case, and for the another case you can find x2 equal to 0 and x3 equal to 1. So for these two different cases you will get if you solve the system of equation, that is very simple, x1 plus 4x2 plus 2x3 equal to 0. So only one equation to solve, so that doesn't take much of the time. So you can simply arrive at these two vectors. So this vector, first vector corresponds to the first case, and second vector corresponds to the second case. So therefore you have two vectors in the null space of the matrix. So now to consider this left null space, you are going to take this second upper triangular matrix that we arrived from this transposed A matrix. So similar steps you follow. You consider one pivot variable and two free variables here. So y1, y2 and y3. So your first equation is y1 plus 2y2 minus y3 equal to 0. And then you substitute similarly y2 equal to 1, y3 equal to 1, 0. And another case is y2 equal to 0 and y3 equal to 1. So for these two different cases, you will have two different vectors. So that is why we got two vectors in the left null space of the matrix A. So these are the steps to calculate your fundamental subspaces for any given matrix. And some other problem, it is fine. How to find this solution?
Can I interrupt you or should I ask my doubt at the end?
Do you have any doubt? And can you wait?
It's a previous question. I have a doubt.
Okay. Yeah, okay, I can ask.
Ma'am, in some questions in the graded or practice assignments, when they ask the column space and row space, there are instances where we've used the row reduced matrix and then told that that is the column space 100. Or, I mean, there are some questions where we've solved it that way also.
See, when you find this row reduced form, the only difference is if you use this row reduced form, you will get unique basis values.
Okay.
Because they form this unique basis which can never be further reduced. Okay. So this 1 to 1 and 1 for 2 may also be reduced into some unique basis, right?
Yeah.
But this row reduced form is a unique basis value. So that's why there is only one difference with the row space of matrix, because in this row space alone, if you use this reduced row echelon form, you can simply take the rows from this matrix itself. So if you use this reduced row echelon form, you can no need to find this transpose of this matrix. So from this matrix A, you reduce it to its RREF form. So from the matrix A to its row reduced form. And do not take transpose of a matrix. Okay. So this is for only computing your row space alone, not for this column space. I'm telling for row space.
Okay.
So at that time, so once you have formed this reduced row echelon form, then the rows of the matrix, okay, rows of this RREF, that is reduced row echelon form, constitutes your basis for the row space, the non-zero rows. Yeah.
So, ma'am, if they ask for a unique basis, then we use that row reduced.
So if it is, if it is mentioned like you need to form this from the unique basis, then you can use this reduced row echelon.
Okay. Secondly, ma'am, one more doubt I had was like here you've taken x2 is equal to 1, x3 equal to 0. So you've got this these two vectors. Suppose if I take x1 equal to 1 and x2 equal to 0 and do the calculations, then probably I may get another vector. It may not be same as this.
No, see, for x1, you cannot assume any value because x1 is your pivot variable, right?
Okay, fine. Yeah. So it has to be x2 and x3, that means.
Yeah, these x2 and x3 alone are free variables, which means they are free to choose. So that is why we are assuming to be 1 and 0. So this x1, we are not giving any values.
Okay, fine, ma'am. Clear, ma'am, now. Thanks a lot. Thank you.
Yeah, okay.
Excuse me, ma'am.
Yeah.
Ma'am, what is pivot variable? Can you explain this again? What is pivot variable and what is free variable?
Okay. So, see, from considering this row upper triangular matrix form, so this pivot is the corresponding row or column that is unique. So it is not dependent on any other column. So the variable tells you that this column is going to be the basis for the other two columns. So that is the pivot variable. So the free variables are x2 and x3, right? So these are free in the sense these two columns, right? So that corresponds to this x2 and x3. Can you relate it in this equation? So this x2 and x3 are free because they are dependent on this pivot entry. So this is the independent variable, that is the pivot.
Okay, ma'am. So
and
column
free variables are
Ma'am, column 2 and column 3 are dependent on column 1, no?
Yeah, correct. So column 2 and column 3 are dependent on this column, first column.
Okay.
That is why it is a pivot entry. The pivot element is the number of independent columns. It tells you. So, for example, how do you find the rank of this matrix? So the rank is the dimension of this column space and also the dimension of the row space. It happens to be same. We have also seen the proofs. Okay. So this rank is the number of independent columns in columns. Yeah. So how do you find this number of independent columns? That is simply from this number of independent pivot variables from this upper triangular matrix.
Okay.
So you know how to find this pivot, right? So this pivot is Yeah, so this element, so beneath the pivot, there should be zeros. Otherwise, it is not a pivot.
Okay,
And
ma'am.
to the
But
left of that element, there should not be no element, non-zero element. That is a pivot. The condition for selecting a entry in a matrix to be pivot is there must not be any non-zero elements below that pivot variable. That pivot element, and there should not be any non-zero variables before this pivot element.
okay, ma'am.
Yeah, see here there is 4, right? So the
Yes,
4
yes.
is in first column, but first row, but is second column. So here
Yes.
we have a non-zero entry. So that is not a pivot.
Yes,
You
ma'am.
understand, right? Yeah.
Yes, ma'am. Yes. Thank you.
Okay. So if you want to find any solution for this given matrix, so the matrix's condition is this AX equal to B to be solvable. So if you want to find such vector, then it should be that any of these rows in this matrix should be equal to all zeros. So how do we do that? We augment this matrix with the vector B, that is B1, B2, B3, and try to reduce this vector to matrix to a reduced row echelon form or upper triangular form, any form you can do. So if you try to achieve that, when you get all 0 rows here, only then we can say that this B belongs to the column space of matrix A. So that you know, right? In order to solve this equation, this B vector should belong to column space of A. So that we have seen, only then it is a solution for this equation. So in this given matrix, the condition is B3 minus B1 minus B2, that must be equal to 0. So when this is also equal to 0, then it is said that all the elements of this rows are 0. So the condition is the B3 minus B1 minus B2 equal to 0. So in case if you are given any matrix and you are asked to find whether this B vector is solvable or not, you just augment with A and then find whether you get any number of non-zero rows. Maybe it may be 2 or it may be 3. And depending on that, you can say that it is solvable. Okay. So that is the condition. And this is a simple example that we have already seen in last revision also. So given any vector. So for this vector, how do you find the projection matrix? So you have a vector available with you. So you just compute this product A transpose and A transpose A. And we can substitute here. So that is how the formula goes, simple substitution of the vectors. So when you do this in calculation, just make sure that the given vector is a column vector. So this should be a column vector. For this, why we have this as a column vector? Because see, for this first numerator, A into A transpose, if you consider this A as a row vector, then here itself you will get a scalar, and in the division you will get a matrix. So that is an incorrect form, right? So even in your question paper, if you get any vector while you're solving for this projection matrix, just make sure that this is a column vector and then take transpose for A transpose and A transpose A. Okay. So after this projection matrix, if you are given any vector, so for projection of B onto A, you can simply use this formula. A transpose is multiplication of this projection matrix with the vector. What should I write? Okay.
Which one?
So I have this simple projection example. So next is the least squares method. So this is a simple example for least squares method. So consider this data points. So this example also we have last seen. So how do we represent this? We represent this using a straight line. So there can be more than one line, right? So we cannot say only this line is suitable. So there may be possibilities of any other line. So how do we select this method? Using this solving this equation. So we need to solve the given matrix using this equation so that we get the best line. Okay. So what is the residual? So residual is the distance of points from the line. So if you choose any line, so from the vertical distance here you have, right? So you compute this distance and that is a residual. So the least square line is the one line which gives you the minimum of the sum of squared residuals. So for example, this line, I'm considering this line. Okay. So if I take this line, So this line should give you the minimum sum of squared residuals. So this is how you find. So this A is an coefficient matrix that is made from your data points X. So this coefficient matrix belongs to the X values here you have, right? So X1, 2, 3, 4, 5, 6. And this is the column vector of ones that is to have coefficient for your intercept. So that is why we have a simple vertical column of ones. So that this is the solution, right? X hat is your solution, wherein the first element will give you the slope and the second element will give you the intercept. So if you interchange this positioning of this column of ones, if you put here, that is in front of the X values, then you will get this here also you have to interchange while interpreting the result. That is it, no big deal. So compute this formula, compute this matrix, and then you have to just find A transpose A and A transpose B. So if you find it, then we can have this two matrix values, and this is a vector with A transpose B. So we have two sets of equations, right? So it is a simple solving linear equations. So 55 theta prime hat plus 15 theta double prime hat equal to 49. And 15 theta prime hat plus 5 theta double prime hat equal to 14. So if you solve these two equations, you can find the values for theta 1 and theta prime hat and theta double prime hat. So that will give you the value for your X hat. So this X hat is your least square solution. So just remember that is how we derived in class also. This is your least square solution. So this gives you the best line. So for this best line, the slope is 0.7 and intercept is 0.7. So
can you go to the slide before? Just go to
yeah.
This before this slide.
This one?
This, yeah. This here you said column vector is A and A transpose.
Yeah, this will give you
so A is a column. So this A transpose should be a. We haven't taken in this multiplication. You've taken A transpose A.
Oh, sorry, I have written maybe wrongly, right? Here. Correct me?
Yeah, it is wrong. That should be, yeah. Then
Yeah,
only
yeah.
we'll get this.
This here I have
4 by
mentioned
4,
it
yeah.
wrong. Sorry for the trouble. So here it should be because if you do that thing, no, here what happens in the denominator, you will get a matrix. You understand, right?
Yeah. So this should be this matrix should. I mean, this should.
So this is a 1 cross 4, and this is 4 cross 1, right? So the product is 1 cross 1.
Right.
Yeah.
But this should be 8. Yeah. So,
yeah. So thanks for pointing that out. I would have just while typing it out, I made a mistake.
Right, ma'am.
Yeah. So you got the point clear, right? So the main point is
yes, ma'am. The point is
okay. Because here this should be this value, and here if I have changed this one, then it would have been clear, right?
Yes.
Okay. Yeah, thanks for pointing that out. So that just a typing error right here. So please everyone note that this in the slide alone it's a mistake, but only this A transpose A and A transpose values are correct. But only thing is the left hand side alone we just interpret. Okay. Yeah. So that's all with this week 3. So once you arrive at this equation, then for any future value of given any X value, and if you are asked to find what is the prediction of that X value, simply multiply, use that in this function, y equal to 0.7x into plus 0.7. Then you will get this value of y from X. That's all. So do you have any queries in week 3? So in your exams, concentrate on this solving using the correct vector notations, and how do we arrive this least squares, how do you place this vector of ones, and how do you interpret the result. That is the main thing. And the one question I have in chat box, so for ax equal to b to be solvable, if we have two 0 rows, then will there be two conditions? Yeah, yes, Akansha, if you have two rows with zeros, then you will be having two different conditions. That is true. Based on the number of rows, non-zero rows, the condition depends. Sorry, number of 0 rows. Yeah.
Ma'am, for this week, we should focus on least squares.
You can focus on this project and least squares for numerical problem solving.
Okay, thank you.
Yeah. Okay, so thank you all. So we can move on to week 4.
Hello, ma'am. I have one doubt. Can you
Okay,
explain, ma'am, how null space of a matrix is perpendicular to row space of the same matrix?
Okay, see, in the null space calculation and the row space calculation, so if you find this vectors of this null space, right? So these vectors of this null space are also going to have the same elements that is corresponding to that of the rows. So that is why we are telling this rows and null space. Row space and null space are orthogonal vectors.
Can't understand,
Because
ma'am.
you can't, let me go to that slide.
Can you open
once.
the second slide, ma'am? Second slide.
Yeah.
You explain
Okay.
there. Yeah, open. Please.
Yeah, I'll go to that slide. So here, right?
Yes, ma'am. Yes, here. Yes.
See, only thing is based on this dimensionality. So this Rn, right?
Yes.
So here the dimension is Rn. See, if you have a vector in this vector in row space, it has a dimension of Rn. It is an n-dimensional subspace. So those vectors in the correspond to the rows of the matrix A.
Yes.
And this null space are also having this product. What it gives you. So if you have a, say, for example, the same matrix I will consider A1, A2, A3. For example, A4, A5, A6. Okay. And so this is a simple A matrix. Okay. And we have this vector x1, x2, and x3. Consider that is a vector. So now, what is the product here? So how will you take this product? So this row is here. So this is multiplied with this column.
Yes.
Column, this is a vector. Consider this to be a vector. So you are multiplying this row with the vector. So this vector multiplies this row. So that is how the dimension is also Rn. Can you understand?
Yes,
the null space. So their product is equal to 0.
Yes.
So that is why a vector, when a row and two vectors are orthogonal to each other, we say that their product is dot product is equal to 0. So from this property, can you relate it? So there are two vectors. So this is vector 1 and this is vector 2. Okay.
Yes.
Yeah. So now I'm multiplying this row vector. No, this is for a matrix. This is a row vector. Yeah.
Yes.
So now this vector 1 and vector 2, their dot product is equal to 0. So that is the case, right?
But
so their dot product equal to 0.
So this is null space, but what about the row space?
And this is the row space of a matrix. So here we are considering this null space from this reduced row echelon form, right? That is from the reduced upper triangular matrix. So these vectors A1, A2, A3, consider these vectors are vectors in the row space. Can you relate it? So this vector is making the rows of this matrix to be equal to 0, right? Man, the product gives you.
Yes.
So that is how we relate this row space with the null space. So row space gives you the independent vectors in the rows of matrix C, right?
Yes.
Yeah, so that is why the number of vectors, so each and every vector in this row space and each and every vector in this null space are orthogonal to each other.
Okay, ma'am.
Can you relate it?
Yes, ma'am. Yes.
Yeah. So
Yes,
similar
sir.
case, the opposite for this column and left null space. Okay.
Yes, ma'am. Yes.
Yeah.
Thank you.
Yeah. Okay. So shall we move on to this week 4?
Yes, ma'am.
Okay. Yeah. So Vishal, can you continue for week 4?
Yeah, thank you. So
Yeah.
I'll share the screen now. Okay. So now we'll move to the next or the last topic of today. So in the fourth week, we have just talked about, in the first lecture, we have talked about the feature matrix. So feature matrix can be defined as such, like if you are having a data set, and if this data set is having a 3 features, like for example, I told you in the starting also, I was having for example, I'm having a data set, and this data set is consisting of 3 features, and this 3 features are like, first one is the what you can say, the power of the camera, or the second features is the RAM, and the third feature is the storage, and then we are having the label also. Okay. So for this, as we are having the label also for this features, like for example, for the first observation, we were having this features, the first feature, the first observation. Yeah, we can write this as a x1 as x1. This we can write it as like,
10 volt.
That is name of the diode. So
I know the diode.
So okay. So the first the data point first can be written in this form, like the first features are 16 and the second or 16 and the third is 64. So in this way, we can like all the data features of one observation can be written in the form of column. Okay, so this and this is how we proceed. So now we can write this like we were having this features matrix. This is A, right? And we were having the labeled value also. So if we are having the labeled value, so we can develop a model. So simply we are discussing about the linear model. So linear model can be modeled as like this, like theta naught can be a dummy value, and then this theta 1, theta 2, theta 2 can be the weight that will represent respect to the x1, x2, x3. Okay, so if there is like theta 1 generally tells you if we are putting all the other things constant, how much change will happen in if we are changing the x1 by 1 unit, how much change this theta 1 will happen. Okay, so this is simply the weight, you can say, correspond to the x1, and this is the weight correspond to the x2, and this is the weight correspond to the x3. So estimated, or you can say that theta can be written in this form. Theta naught, I already told you, it's a dummy value, and from theta 1 to theta 3 are our weight, or you can say the parameter. Okay, so we can write this error as this form, like the actual one or the predict. The actual one was what? Actual, we can write it in this form, A into Q, right? So A was our features matrix and Q is the parameter. Okay, so AQ minus Y we can write. 1 second, I'll just close the window. Yeah, so yeah, error can be written in this form, the actual minus predicted chi-square, as we are using the least square error. Okay, so we can do this AQ minus Y. And this AQ minus Y is simply the actual minus predicted, you write, or the predicted minus actual. That's why we are squaring here. So A is simply I have written in the form, if we are getting confusion, how we generally write this feature matrix. This is in the form x1 transpose x2, x1, x2, x3 is all are the column vector. Okay.
Sir, you have
Yeah.
written here predicted minus activity, sir. That is actual, I think, no?
Yeah. It's a mistake, sorry. 1 second. So this is actual. Yeah. So error we are already doing. So predicted minus actual, that can be written in the form of matrix as AQ minus Y transpose of AQ minus Y. This I already, you are aware of that, how like in the matrix form we can write this square in the form of A transpose A. Okay, so this is how we have written, and after doing some sort of matrix calculation, we can come to this conclusion. This I guess is no need to prove. We can prove also, but this has been talked or proven already in the lectures also. It's not in the lecture, but in the last session and all, we have proven this also, how we are coming to this conclusion, theta as A transpose A inverse A transpose Y. So this is a pretty, just you have to do a simple calculation, and then you have to get through the matrix calculation. That after doing that, we can come to the weight, like you can sort of know regarding the weight. And this can be this is a simple like a model to build up a linear regression model, because we are taking all the weight in the form of all the weight, or you can say the data set, whatever we are taking in the form of first degree only. We are not transforming anything, so we are just taking out whatever the x1 or the data set we were having. We are just putting it in a we are taking some sort of weight, and then with that weight we are just multiplying and converting that into a simple linear model. Okay, so we are not transforming the data set, we are not doing anything, we are just building a simple model to fit a straight line, you can say, to a data set whatever we are having. Okay, so this is simply this error. So to build or to get a good models, what to fit a straight or to fit a better line or better curve to that data set, what we can do, we can minimize that error. Okay, so while minimizing or maximizing the likelihood function. Okay, so this is one method, like the least square method, to get the good fit line to the data set to come to get the predicted value. Okay, and in this polynomial regression, what we generally do, we are having the data sets. Okay, and we generally do some sort of transformation. Like in the polynomial, we can do the squaring of all the data set, and with that squared value, we can have again a new feature matrix. Like for example, we were already having the 3 features matrix. Now we can square the value or cube the value, sort of like anything we can do with those data set, like x1, x2 also we can do. So we'll be having a new features added. Okay, so whenever we'll do such things, like whenever we are increasing you can say the not the you can say the not the dimension, if we are increasing the power of the data sets. Okay, we are doing, like for example, if I've taken x1, x2, and then x1 square I did, like some transformation we are doing the data sets. Okay, so and with the help of those data sets, if I'm doing if I'm trying to build some sort of model, then that will come under polynomial regression. Okay, and simply regularization is a bit a basic tool, or you can say a basic tool that generally help us to reduce the sensitivity. That means we are, see, for example, if I am having a very complex data set, like if you'll plot, if you're having the data set, and after doing the transformation, or if you're not doing the transformation also, if you have plotted that graph, or you have done the scatter plotting of the plot, and after scatter plotting, you can see that the data set is very vague, or you can say the you can say the curve, whatever you want to take, like the curve you want. After developing the model without using the regularization, that model or the curve was too fitting, very much overfitting to that the data set. Like if I'm having the data sets such like this, so this was too much overfitting to that. Like for each, if I'm having some sort of the data set which are very much not correlative to the bunch of data set also, so this curve was taking considering of that data set also. So okay, so what in the regularization, what we are doing, we are just sort of reducing those things. So we are just reducing the sensitivity. So if there is some sort of data set which are very much different from those group or the bunch of data set, so we need not to give the attention to data set also. So this is what generally I'm taking a broader perspective, what generally regularization does. So it generally helps us to reduce the data, like overfitting. Like if it will give you that type of curve that will not react much to one data set, or those data sets which are not very much correlated, or which are very much different from that or you can say the very much vague data set. So this generally doesn't reflect much to those vague data set. Okay, so this regularization, in that regularization generally we add some sort of constant in that model to help us to reduce or to help us to develop some sort of value in that curve, so that it will not reflect or react to each and every data set. Okay, this is what generally we do in the regularization to reduce overfitting or to improve some sort of like underfitting also, you can say. So this is simply the regularization. Maybe you'll be read in the further courses, but it's a broader perspective to why we are generally using the regularization. Okay. So in the first unit, we were just talked like about the linear regressions, how we are building a simple model, and with the help of some sort of transformation, how we are developing a polynomial, what you can say, the polynomial regression model. So this is what we have talked in the first lecture. Okay. In the second one, in the further weeks, not in the further weeks, not the further lecture, we have just talked about the eigenvalue and the eigenvector. So eigenvalue, you can say, or the vector, when if like, for example, if I'm having some sort of like one vector, okay, and after doing some linear transformation, like if I'm multiplying linear, like matrix multiplication, simply you are doing some sort of transformation. This AX is what? Simply you can say like in the mathematics, in the calculus, what you do is, if you are having of fx function, you're just putting x value, and then if you are getting y, like y, if y is equal to fx of some function, so what you are putting some value x and you are getting the y. So here also you are just transforming the vector with the a, or the multiplying with the a matrix, and then you are getting a another vector. Okay, so after you getting that vector, if that vector is simply the, you can say, the scalar form of that vector, then you can say that the scalared value is the eigenvalue, and the vector that you have done the transformation, that is the vector, and the scaled value is the eigenvalue. Okay, so this can be calculated with a simple example. Like, for example, this is the most important thing, that is ax is equal to lambda x. So if you are doing some sort of transformation to that vector x, and after doing that transformation, if you are getting some sort of scalared form of that vector, okay, that scalar value is the lambda. So lambda is simply the eigenvalue, and the x is the lambda, x is the eigenvector. Okay, and what's the procedure, or you can say the characteristic equation for this? Simply we are just putting everything in the one side. So a minus lambda I to the power, like, into x is equals to 0, and this is the, if you will do the calculation, this ax, a minus lambda I is the characteristic equation, and after solving this, you will be able to get the eigenvalue, and corresponding to each of the eigenvalue, you can get vector also. And what was the motivation why we are doing this? This is not important, but for the brief purpose, like I was telling you, there, like, it's a simple, like, if you are having some sort of system, and in that system, if you are having more than 2-3 variables, and the change of one, like, for example, if I'm having system PV is equal to constitute, I've read about the Boyle's law. So in that Boyle's law, in that Boyle's law, so if you are having the system, in that system, it depends, like the system generally depends on the pressure and volume. In that pressure volume situation, if the changing, like, for example, dp by dt generally depends, if that change of one variable depends on the other, depends on itself also, and depends on the other variable also. Like, for example, I've taken you, I took you one example, du by dt is if I'm having one system, in that system, there is two variable u and v, and in that u and v, that, so the change of u with respect to time depends on u also and v also. Similarly, the v is another variable. Okay, and that v also depends on the change rate of change of v also depends on the another on both the variables, so u and v. So this ub can be written in this form as w. So w can be represented as ub, and both the ub are the vectors. So the, if you will, I'm just telling you why we are why we generally, how that eigenvector and eigenvalue can be helpful in this physical system, where where it's very difficult to get the conclusion. Okay, so where the w can be represented in the form of uv, where u is a one sort of variable and V is the another sort of variable. So if we are differentiating the matrix differentiation, generally each of the elements of that matrix generally gets differentiated. Okay, so this is how that W transpose then will be represented as du by dt and dv by dt. Okay, and W transpose yeah, so W transpose is what you differentiation of U and differentiation of V. So this du by dt can be represented from this matrix. Okay, and this matrix is what 5U minus 10V and 6U minus 13V. This is sort of one example, and this can be written in this form where A will be our matrix and V U V can be represented as U, and B we already have written. So W is a what you can say the vector that consists of U and V. So W can be written here. So it's a simple example of a ODE, or you can say the differential equation. This is a simple differential equation where dW by dt is simply the dW by dt is equals to some constant, that is the A, times its on variable. Like here I'm giving you one example, like in the normal case, or you have read in the SHM motion, generally you came to, like, whenever if you're having some sort of spring and all, if you just what you can say move the or you can say, yes, if you move, it will depend upon the change of the what you can say the change, how much you are moving that what you can say that block. Also that also it will depend upon the change of that. Okay, so this is some sort of, you can say, just I'm showing you, if this is a vector, this is in the form of totally matrix. If we are having in the form of calculus, simple calculus, how generally we solve? So if we are having dy by dt is equal to, or it's a decaying function simply, not decaying function, generally in the decaying function we'll be having negative of that, like in the radioactive and all. So here, but we are simply the exponential function, dy by dt is equal to k times y. So this we can solve with the example simple. This is a simple ODE differential equation that can be solvable. So here y is equal to k times e to the power pt. Okay, so this is almost similar. This is how in the calculus we are solving, and similarly we can solve here also. So y dash can be equals to k to the power e to the power lambda. W dash is simply what? A is a matrix, and W we were already representing W as UV. Okay. So W dash we already have. So W we can write from W. Yeah. So W can be written from the W dash, right? So if A we already know, and we can replace the W, and then we can equate both the equation. After equating both the equation, will come to know that e to the power lambda t and e to the power lambda t will get cancelled. So we'll be having a k equals to k lambda, and k is simply a vector. So this can be written in this form: ax equals to k lambda x, right? So if we have to solve, like for, see, if I'm having this A matrix now, so we were in the starting we were asked to solve this a very different problem, like you can say the difficult problem. And if we are having here, what, see, if I'm having this matrix A only, and if I know regarding the eigenvector and eigenvalue, so what we generally need here, we generally, if we have to solve W, we generally need k vector and the lambda vector. K and lambda can be calculated from its eigenvalue and eigenvector. Okay, after putting this here, will be able to at least get the will be able to solve this difficult problem with this help of eigenvalue and eigenvector. So that was the simple motivation, we can say, behind why this eigenvalue and eigenvector is pretty like popular and all. This is what you can say the motivation behind that. So from the starting first two lecture, mostly important for the exam is to know to calculate the eigenvalue and eigenvector, and the important properties that will read regarding the diagonalization and other stuff, like for the how that symmetric matrix are what you can say orthogonally diagonalizable. So those will read now. So till now, if you are having any issue, you can ask. But yeah. Okay, so we'll move to that next part of this. The next part is in the third lecture. We have been talked about the diagonalization. So in the diagonalization, we'll just go through some of the basic important properties of the diagonalization. See, for example, I'm having a matrix. Okay, so if I'm having an n cross n matrix A, is very much similar to, we can say that A is very much similar to B if there is an invertible matrix P. Okay, so this is not diagonal. This is a pretty simple example when A and this A and B is similar to itself. Like how can we see that, say that A and B are similar? So if we'll see regarding the determinant, trace and eigenvalues of A and B, we can say A and B is very much similar to itself. And when this B, if we have to diagonalize that A matrix, and if we are able to get some sort of P inverse and P such that B equals to the diagonal matrix of the A, like B becomes a diagonal matrix, and that diagonal matrix consists of the diagonal of the consist of all the eigenvalues of the A, then we can say that A is able to, we are able to diagonalize A. Okay, so this was the basic thing. Like if A and B are very much similar to itself, if we have to calculate anything regarding the B, we can calculate. If we have to calculate anything regarding the A, we can calculate for the B, and then we can say, like if we have to calculate the determinant of A, we can calculate directly the determinant of B, and then we can say, because both are similar matrices. Okay, so and if that B get replaced with the diagonal matrix, and that diagonal matrix consists of all the eigenvalues, that all the eigenvalues at the diagonal of this matrix, then we can say we are able to diagonalize A. So A is simply n cross n matrix. A is diagonalizable if it is similar to a diagonal matrix. Like for example, here in spite of B, we are having a diagonal matrix, and A is diagonalizable if there is an invertible matrix P. That is for yeah. So if we are able, so we'll see what are the important, what you can say, the features, or what are the important things that are required to make a matrix diagonalizable. Okay. So this is the simple steps that to calculate. If you have to, like for example, you have to calculate the diagonalization of this S inverse S equals to this diagonal matrix. So what you can do, you can just calculate the eigenvalues of A, and then you can calculate the eigenvector of B, eigenvalue of A and eigenvector of A, and then you can write this S in the form of like this, and then you can calculate the P inverse or S inverse, whatever you want, and then you'll be able to get a matrix that will consist of the that will be a diagonal matrix having eigenvalues at its diagonal. Okay. And the important things regarding when you'll be able to diagonalize any matrix. Okay, so if any n cross n matrix with distinct eigenvalues, then it is diagonalizable. So that is pretty sure. If you are having n matrix, if you are having n eigenvalues, and all those eigenvalues are different from each other, then for sure it's a diagonalizable matrix. Okay, and if and why we are doing this, because the matrix multiplication becomes very simple. Like you would have read regarding the Fibonacci series and all. So how that diagonalization application helpful in calculating the kth term of the Fibonacci series. Okay, but one important thing is, if A has a repeated eigenvalues, then it may be or may not be diagonalizable. If you are getting if you are having, like if you have the sufficient eigenvector, then you will be able to diagonalize. So the thing is how many sufficient eigenvectors you should need. Okay, so the one very important thing is, you would have, see, one basic thing is, if you are having all the eigen values as distinct, then you will be able to diagonalize this. That is for sure. But if you are having some sort of repeated eigenvalues, then how can you tell regarding that? For that, you have to read one concept, that is AM and GM. If like AM is simply the algebraic multiplicity of that matrix, and that geometric multiplicity of that matrix. If you know regarding that, or you can read from some places that if that GM and that is the one of the most, like you can say, the sufficient and condition to say regarding the diagonalization of the matrix. Okay, if that AM and GM is equal, for each of the root, or you can say for each of the eigenvalues, then you can directly say, yeah, so this is a diagonalizable matrix. Other than that, if you can't say directly, like if you have the sufficient vector for the repeated eigenvalues, also if you are getting some sort of eigenvector which are not dependent, then you can directly say it's a diagonalizable. But if you directly say from the eigenvalues only, you can't directly say if you are having the repeated eigenvalues. Okay, so for that you have to calculate the GM and AM. That you can that is not like here taught regarding that GM and AM, but you can read from some other places regarding the geometric multiplicity and algebraic multiplicity. If both are same, then you can directly say it's a diagonalizable matrix. Okay, otherwise if you are having a distinct eigenvalues, all the eigenvalues are distinct, you can directly say. This is also same thing, like if A has a repeated eigenvalues, then its eigenvector may or may not be linearly dependent and dependent. Okay, and this is the one example, one application of that, why we are doing the diagonalization. If you have to perform some sort of if you have to calculate the A to the power kth term of that, not A to, if you have to know regarding the A to the power kth matrices, then you can directly do that application to the diagonal matrix, and then you can calculate whatever you need, like trace or determinant or anything. If you want to calculate anything, if you want know regarding the sum of the properties of the A, you can do the same operation on the diagonal matrix, and then you can get to know regarding the properties of that matrix. Okay. And the fourth lecture, we have talked about the Fibonacci series. That is not important at all for the exam, because we can't directly ask regarding the value. But I'll just talk a brief about the Fibonacci series, how it has been talked. Like if you have to know regarding the A, F, K plus second term, like for the K plus second term, we can say like if like in the Fibonacci series, what happened, like the last two terms get added. So if K plus 2 will be equals to F K plus 1 plus K. So that we can write in the form of vector. Okay, so that has been written in the form of column vector, you can say, and UK plus 1, it's simply this will get added. So K plus 2, FK plus 2, FK plus 2 is what? FK plus 1 plus FK. So this can be written in this form. And this matrix can be changed to a matrix form, like 1 1 0 1. So if you'll multiply this, you'll get the same thing. Okay, so UK plus 1 is simply can be written in this form, A into UK. A is this, it's this matrix, or you can say the transformation matrix. Okay, similarly, yeah, so and U naught was simply you can get it from the starting portion, like U naught is 0 1. Okay, so AK is what? AK is simply, you can calculate also, if you want to know how this came, you can do the U square also, like A into A you can do to the into U naught, you'll get to know it becomes A square, and this will be U 2. Okay, so a U to K or the kth term, how will you get that? So that is simply like UK is what? If K plus 1 upon K, like FK, it's a column vector, right? So AK is what? If you have been asked to calculate the kth term, what you can do? So you can do the operation on A with the help of diagonalization, and then you can directly say, because A, the matrix we already have. Okay, so after diagonalization, we can get the diagonalized value, diagonalized matrix. And if you have to get regarding the kth term, we can do the some sort of like the if we have been asked regarding the A to the power kth, if we know regarding the properties of the A to the power kth matrix, what you can do, you can do that sort of calculation on the diagonal matrix. Okay, you can multiply it kth times. What generally happen, if you are having only the diagonal matrix, you can do it very simply, and then with the help of that matrix, you will be able to calculate the kth term, right? So here it's a Fibonacci series, simply a use, or you can say the application of the diagonalization that has been talked in the earlier lecture. Okay, so you just with the help of diagonalization, you can do that. You can get the AK, right? So, and then you can put it here and you can get the kth term simply. So this is not important for the exam, but yeah, just you can, for example, you will be able to, like, it's a simple application of the diagonalization. Okay, and in the last lecture we have just talked about the symmetric matrix. So like if you are having the symmetric matrix, you already know if you are that if you have the symmetric matrix, then if A is a symmetric matrix, then A equals to A transpose. That the transpose of A will be equals to the A. And if you are having there are some important properties of the some important properties of the symmetric matrix. That is, all the eigenvalues of the symmetric matrix will be real, and if that matrix is a skew symmetric, then all the values will be either zero, all the eigenvalues will be zero, or the what you can say, the complex. So for the real symmetric it will be real, and for the skew symmetric or the skew symmetric it will be zero, or the complex value of the complex eigenvalue. Okay, and the eigenvector corresponding to the distinct eigenvector are linearly independent. Written correct, incorrectly, independent.
Independent, sir.
Yeah, so it will be linearly independent. Okay, and if you are having eigenvalues which are repeated, then in that case those two vectors will not be linearly independent, those will be linearly dependent. Okay, but for the distinct eigenvalues, the eigenvector will be linearly independent. So any two eigenvalues from the different eigenvalues are orthogonal to each other. That is pretty known. And yeah, so if you are diagonalizing that symmetric matrix, like all the symmetric matrix, you'll be able to diagonalize. Okay, and you'll be able to write in this form Q into, like if you are having that A matrix. So it's a simple, like represent the same representation. Like you can write in this form also, Q transpose AQ. Okay, this will be equals to A. So this also, because here this all the symmetric matrix are generally orthogonally diagonalizable. Okay, so here the Q or Q transpose, whatever you are getting, it will be like here Q transpose will be equals to Q inverse. That is why we are writing like this. Okay, so here that Q transpose will be equals to Q inverse. So this matrix, this whatever in the earlier cases we were getting this S, or we can say the P, this S or P we were getting earlier. Here it will be what you can say, the mod, or you can say the length will be one of this each column, and each of the column will be orthogonal to the other vectors. Okay, if we are having the distinct eigenvalues. Okay, so that's the what you can say, the procedure is same here also. How to diagonalize any of the matrix, you can calculate the eigenvalue, you can calculate the eigenvector here also. First, one important thing is you have to normalize that eigenvector so that the magnitude will be 1 here. Okay, rest everything is same for the diagonalization of the symmetric matrices also, like you were doing for the earlier cases, for the any other cases. And the important thing is here is, you should be from this week, the important thing is you should be able to calculate the eigenvalue of simple matrices. If you have been asked regarding the 3x3 matrix also, you should be able to calculate the eigenvalues of that matrix, and you should be aware of the properties of the matrices. Like for the properties of the real symmetric matrices, you should be aware of that. You should not you should not go through that Fibonacci sequence and all. It's not important at all for the exam, because the application of diagonalization. So simply you should be aware. Will be checking regarding the awareness of the properties that regarding the diagonalization, properties regarding the real symmetric matrix, and you should be able to calculate the eigenvalue. That's it, I guess, from this week. And yeah, so if you are having any doubts, you can ask regarding this week. Yeah, if you're having any issue, you can ask. Otherwise, so the important part I already have told you, to be able to calculate the eigenvalues and all for the 3x3 matrix or 2x3 matrix also, and you should be able to know regarding the properties of each of the things like symmetry. That already I've read, like wrote in this notes. You can go through this notes once again before that exam, and you'll be able to solve that problem. Okay, so if you're having any issue, you can ask. Otherwise, we'll meet on the Monday or Sunday for that other weeks.
Sir, what is the entire purpose of diagonalizing a matrix? I mean, I couldn't understand. We are diagonalizing it, but why do we diagonalize?
See, if we are able to know regarding that diagonal matrix, okay, that is similar to a matrix, a very vague matrix which we are having. And if I am able to diagonalize that matrix and I know regarding that diagonal matrix, which one is similar to that. Okay, so if we are able to do that, if we have been like, for example, in the Fibonacci series itself, we have to know regarding the kth term. So with the help of diagonalization, we were able to know, right? So
Yeah,
that
so
can be the one application. Yeah.
So basically, we do a diagonalization to find a diagonal matrix so that the calculations become simpler. We are able to manage it easily. Is it, sir?
Yeah, that is the one of the most important example.
Okay.
Sorry, the application of that. Yeah.
Okay. So diagonal matrix is a matrix which is similar to the given matrix, which is which has diagonal elements. So the calculation becomes easier. That's the right way of understanding it, right?
Yeah.
Okay.
Yeah.
Okay, sir.
Sir, why do we need orthogonally diagonalizable matrix then? Like
no, if you're having real symmetric matrix, so you'll get that orthogonally diagonalized things. Like for example, see, in the normal matrix, what we were getting, the inverse matrix we were getting as the like only the vectors form, right? But here, whatever the eigenvalues we are getting in the form of if we are having a symmetric matrix, what we are getting, that eigenvectors we are getting is orthogonal to each other, like they're perpendicular. Okay, so that is why we are saying if I'm having a real symmetric matrix, that real symmetric matrix would be orthogonally diagonalizable for all the cases. This is for all the cases with that. But only the thing is, condition is the matrix should be symmetric. And if that matrix will be Hermitian and all, then it will, that orthogonally will get replaced with unitary. You have read regarding that. We'll discuss in the next, or you can say the Monday's session.
Hello, sir.
Yeah.
So we are doing diagonalization to make the calculation easy. The SVD also serves the same purpose, right? For any M cross N matrix.
Yeah, SVD also helps in that.
Okay. So for N cross N matrix, we do diagonalization, and for M cross N matrix, we use SVD.
Yeah, if you are having some sort of rectangular form of thing, then we can use SVD.
Yes. Okay.
And the third PCA we use when the dimensions are too high, right? So we reduce it to N and then do the PCA.
In PCA also we use the concept of SVD only.
Yeah, but that is for a matrix which has very large. Yeah, that's what. Yeah.
So in this, can we then say that we have two special kind of matrices like similar or real symmetric? Then they are diagonalizable. That's the takeaway.
Yeah.
So, and then that if these kind of matrices we find and these are diagonalizable, then we can use it for further
correct, for
calculation or whatever application in machine learning. Okay. Okay, right.
Okay, then I'll share this file, like we'll share this file and to everyone. You can read through the important properties of this. And then we'll meet in the next session on the Monday for that from week 5, 6, 7, 8. Okay. So thank you everyone. Good night.
Sir, one thing, is it possible, like you have given the important things to consider in each week, can you give the for all weeks prior before the sessions itself so that we can study?
Prior means like how can like we'll be having session on Monday itself. So in the Monday we'll be sharing regarding the 5 to 8. Or you want now itself?
Yeah, sir. If you can like share it before that itself, like you must have already written it somewhere, right? So if you can share that so that when we are doing revisions, we'll focus on those points.
Okay. So for the PCA portion, I can give you. Okay, it's already uploaded, right, Amrita ma'am? For the last revision session, we already uploaded, right?
Yeah, I think so. So for the quiz revisions, we are given the revision slides, right? Quiz 2 revision slides in the
Okay,
portal.
I'll refer that.
Yeah, the slides will also. This slides will also will be uploaded today, and the for the portion like for the 5th to 8th will be in the Monday itself. Will say that. Okay.
Okay, then thanks all for joining.
Yeah, thank you everyone for joining.
Thank you, sir.
Thank you, sir. Thank you, ma'am.
Okay. Bye, everyone.
So I'll tell them to close.
Okay. 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 Bye, Vishal. Thanks.
Yeah, bye.